So once again, I want to welcome all of you to our last lecture for the program, the module, Statistics for Business Analytics. We want to apply logistic regression today. Everything about logistic regression will come to the fore. Remember that logistic regression happens to be one of the classification methods. It is, technically speaking, it is a supervised machine learning algorithm. So the machine learning algorithm, the supervised version you shall do next time, they will not teach you, but they will set you questions and things related to it. I can promise you that top level papers and a lot of PhD works and master's works have been done using this method. And I can promise you that most of you are likely to use this. I could count like about 30 to 40% of you, probably even 50% of you are going to use this for your dissertation, longest thesis. We shall apply it to the disease data sets. Okay. I labeled it as demo logistic. This disease data set is something that all of you are aware of. I'll be toggling between the Python notebook, the Jupyter notebook, as well as the slides, so that you can see what I am doing under both situations. So let me just go quickly to the Jupyter notebook so that you can follow what I am also saying. So in the Jupyter notebook you have to load the data set, which is demo logistic. You will notice that there is a dependent variable or a target variable. When you look at the slides, the target variable is the disease, whether a person is diseased or a patient is not diseased. And the idea is that you want to predict the probability of being diseased or not being diseased based on your age, which is a continuous integer variable, and gender, which is a binary variable, categorical, and smoker status, which is also categorical. So the features are just three. But in real life and in your thesis you'll be doing, the features will be quite a lot. All right. So we can examine the effects. So there are two things that you can use the data for. In machine learning, you can use it to do prediction. In statistical methods, not machine learning approaches, you can use it to establish causality. So there are two things you should know, and this will come up a lot when you are writing your dissertation. All of you have topics, I presume. Do you all have your dissertation topics? So in one of them, you'll be establishing causality, okay, or establishing a relationship or association, impact. So some of you are looking at the impact of A and B, impact of X and Y, and things like that. This, if the dependent variable is binary, categorical, obviously, this is one of the things that you will baseline your work. If you are using machine learning, this is still considered as a prelude to either using random forest, support vector regression. No, this is a classification. So random forest classifier, support vector classifier, decision tree classifier, ADA boost, CAT boost, GB boost, all of the boosting techniques, you could be using them. All of the artificial neural networks, they are classifiers. You can use that. The dependent or the target variable, I have called it disease underscore bin, where the bin represents binary. And is equal to 1 if a patient is diseased or 0 if the patient is not diseased. We are looking at the influential factors or the features which are known as, okay, when you're looking at influences, then you're looking at causality. When you're looking at features or predictors, then you're looking at prediction. How likely it is for a person to be diseased given the age, the gender, and the smoker status. That is the essence. So I want you to consider the classification or the classifier model as classifying each person using a threshold. Okay. So the threshold is that the particular target variable is 1 if the probability of the presence is 50% or 0 otherwise. So you can use this approach to classify. We did this last time. If the probability is 50% or more, okay, then the classifier will predict positive or 1 to indicate that a person is diseased, or it will predict 0, okay, which is a negative prediction to indicate that a person is not diseased. And like I said, this is exactly what transforms probability into classification. We did that last time. It tests for predicting the presence or absence of the disease. Okay, we'll come back to this. Now I'm taking you back to the Python, the Jupyter Notebook. I want you to look at the codes. We have them already. Now, you might be saying to yourself, how did I write these codes? How do you do these codes? Also, when you are, for example, writing your dissertation or something. Now, you will get question on this without a doubt in an exam. Okay. But you will not, I will not ask you to run these codes in an exam. But in your thesis, you will run these codes too. Yes. But I'm teaching you both today. So normally, before you do any of this, you have to, once you've learned it, you go by what you've learned. And what you've learned is that you got to import a lot of libraries. And one of the libraries is the pandas, the numpy, the pyplot, the scikit-learn matrices. You can use that because those will help you to do a lot of analytics when it comes to logistics. So things like confusion matrix, you have to get that there, classification report, ROC curve, AUC curve, mean absolute error. Okay. Even logistic, the log loss, okay, the logistic regression itself. I'll talk a lot about training and testing. And then finally, the stats model itself. So let's prepare the data. The first thing you do is you prepare your data. Anything you do, any machine learning work you're going to do, you got to prepare your data. Okay, so that's the first thing you do. You prepare the data. So here I'm giving some couple of instructions. Load and prepare the data. How do you do that? You import your pandas. Pandas is already imported up here, so you don't necessarily need to even run this code. Can remove this one. Okay, once you run the first one, run this one, by the way. I just did that. Okay, then you can load your data. Okay, now this shows that I want to show the first 4 observations, but let me just make it 10. Okay, so I load the data. I asked it to show the 10 observations. There you go. It is showing the 10 observations starting from 0 to 9. And you can see that the first person, the data shows that the first person is diseased and the person's age is 43, he's a male and he's a smoker. The second person is not diseased. The person is 18 years, he's a male and he's a smoker. And then on and on and on and on. So this gives you a bit of initial look at the data. We know this already. But the next key important thing is that, as you can see, these values are actually categorical. They are text variables. They are strings. And logistic regression, if you want to do it well, you don't need to work with string variables. The good thing about the R software is that R software can actually sense and do that. And I think I did that the last time with you when I was running multiple regression. But for logistic regression, you need to code them as 0 and 1 for those that are binary. For those that are numeric, you leave them as it is. So you encode the target variable, which is also binary here. And it's also text, actually. So you encode the target variable and give it a new name to it because you don't want it to contain the text. And like I said, machine learning algorithms will require numeric input, 0 and 1 for logistic. So the disease, I'm going to code it as disease bind. And then I indicate that from the DF data set, that's the name I gave to the data set, DF. I want you to call disease as 1. Okay. If a person is diseased, give a code name of 1. And if the person is not diseased, give a code name of 0. Okay. When I run that and I show the data again, you will see that it will reflect those. The next one. The next one is to do the same thing for the categorical variables. So here, I create a new data set, okay, called DF encoded. And from the DF data set itself, all the categorical variables, together with even the feature, the target variable, the dependent variable, okay, I'm going to recreate a new data set called DF encoded. And wherever it has something like, and this is very important, this code here is very important with it being true. If a particular code is gender and the gender is male or female, as you can see here, if you don't drop first code true, if you don't use this command, okay, what it's going to do is that it's going to generate gender male and gender female for you, which doesn't make sense because you need one of them to be the reference category. So one of them will have to be in the thing, the other will not be in the thing. One of them have to be 0, the other will have to be 1. But other than that, it's like you are making both of them 1. Okay, so that is why you say that drop the first one. So the first one that will come is the one that will be dropped. So if the first one is, say, male, that will be dropped. All right. The next one is that after you've done all of this one hot encoding, anytime there is a comma, you instruct the code that whenever you see a comma, make it a dash. So here, replace a comma with a dash. So you see that in my slides, okay, you will notice that some of them, they are called disease underscore bind because I've made it like that. And then you will have the next thing is to identify which ones are the features, which ones are the dependent variables, which ones are the independent variables. So here, identifying the predictors and the target is very easy. You represent all the predictors by a matrix called X. And that is simply just saying that out of the DF encoded data, drop disease bin, because disease bin is the target. So drop disease bin and everything else that is left become the X, which is the independent variable. The next one is to now say that out of that same data set, wherever you see disease bin should be the Y, because that's a target variable. Then you convert everything to float, okay, or to numeric, okay, variable. So all the X's are coded like that. Now I want to show you how the DF looks like now, okay. Actually, let me not show this first. Let me just run this thing as it is here. And then let me also show you the DF. Let me just show the head. And just show just the first 5. You can see that now the disease has been coded as what? 0, 1, as you can see there. And now, if I should show the actual encoded, the DF encoded, because the one that captures all of them, you can see that the disease has been shown as 1. So clearly, and now you can also see that it has created not what we had before as gender, but now it has created gender male and smoker status for smoker. So the true here means that whatever you see here, the first person is a male, that's true. Second person is a male, that's true. The third person is a female. Next person is a male, and then it continues like that. It recognizes the true and the false as 1 or 0. So the data has been prepared. That's what we mean by preparing the data. Now, in machine learning, there's something, if you will never be taught, there's something you will learn called training and splitting the data. It's a very, very extensive work which you will learn. By all means, I'll teach you in next semester. But just understand that you divide the data into 2 parts. The first part is called a training data set. And it's usually 70%. And the rest, which is the 30%, becomes the testing data set. What is a training data set? It is what you use to build a model and to build a model alone. So whatever model you're building, whether it is an artificial neural network, logistic, or anything, you use that 70% to build a model and you show all the evaluation matrices and everything. But if you want to know whether the model you have built is correct, you don't use that same data set you had. You use the other one, which you didn't even include in the first one, the testing data set. As the name sounds, you use it to test. So it's like you do. So that testing data set becomes a new data set where the model has not seen before. And now the model needs to use what he has learned to actually do that. A typical example of looking at this is like a mock exam and an actual exam. So the mock exam is the one you use to train. You train the student, will solve a lot of past questions, mock exam, train. Then in the actual exam, which is a test, the 30% test data, that is the exam they haven't seen. So that is sometimes called unseen data. You want to look at the performance of the student or the student on this unseen data. So whatever you do, you split the data into two. And the reason why you got to do this splitting is because a model has to be evaluated against a data set it has never seen before. Otherwise, it will copy. It will copy. The model may appear to be performing well, basically because it's memorized, it's copied the training data. And this copying is a very popular word in machine learning known as overfitting. You learn that. Okay, so look at this here. I have the X train, which means that the dependent variables, which is the X, I have 70%, which are the train. And then I also have X test, which means the 30% out of the 100%, that 30% of the data, we are creating a dependent variable for it. They are a portion. So it's like your normal observation. So if your observation is, say, 50, okay, 30% of that, 70% of that is probably going to be, I don't know, 70% of 50 observations, and then the rest becomes 30. And you are doing this for both the target variable as well as the predictors or the features. So you can see that you are doing it for both X train and X test, as well as for Y train and Y test. Okay. The command known as train test split will do the whole thing for you. As you can see, X is the independent variables, and Y is a dependent or the target. And you can see that the test size is indicated here, not the train size, but the test size. And the test size is given as 30%, which means that the model will recognize that implicitly the train is going to be 70%. And I've also put a random state of 42. You can use any number, any integer will work. Okay. It ensures the 42 randomness ensures that the splitting is always the same anytime you run the code. Other than that, if you don't do that, okay, anytime you run, it will do a kind of simulation and give you different results. So it's still going to be 70 against 30, but some of the observations will move and split and go and join another. Some of those that were in the 30 before will go and become the 70 and all of that. But here you want it to remain. Okay. So run your splitting. Okay. It's something you do automatically. Then we are now ready to run the logistic regression. Now you can see here that I've put inference because the logistic regression we are going to do, we are doing it as if we are doing causality, not prediction. Causality. We'll come to prediction later. You got to choose which one you want or both you want. So here, I add a constant. Okay. I'm going to show you the logistic regression before I come to the constant thing that I'm talking about. Now, when I come to the modeling, you will appreciate it. So don't worry. Okay. So I add a constant, like a normal regression. What do you have? You have the dependent variable being a function of the beta naught plus beta 1 x1 plus beta 2 x2 plus error 10. This is a regression. Okay. Now, this constant here is what I've indicated that you should add it there. So constant should be added. Okay. The next one is you create a logit model. And the logit model, last time we looked at it, but I'll show you properly again when I'm about to formulate the logit model. And please note that you will use this same thing in your thesis, in your dissertation, whatever you see today. So like this command will create the logit model, okay, where you have the stats model, okay, dot logit. The dependent variable comes first, and then the independent variable comes second. Now watch it. You can see that the independent variable is this one, x underscore sm, which is coming from the top here. And that is the x, but just that we've added a constant to the x. So it's all the x plus a constant. And then the result will be shown after fitting the logit model. Okay. Here, I've indicated that don't display the result for this yet. We go to the next part. I'm just putting all the coding together before we run it. The next part is that when you have done the whole work, I want you, Python, to generate the full regression table. I want you to include the coefficient, the standard error, the z-statistic, the p-value, as well as the confidence interval. Give me everything. Give me everything. And call it star summary. And it should come from the results you had from the logit model above. Next, I want you to also give me the odds ratio. Last time we looked at the odds and the odds ratio and the log of the odds. So I want you to give me the odds ratio. And I want you to use the coefficient to compute the odds ratio. And this is the formula for the odds ratio. Also, I want you to give me the pseudo R square. We'll talk about it. The pseudo R square is just like the normal R square in a regression. And there are several of them, but I want you to give me the McFadden R square. The way you calculate the R square is this, and using this formula. I'll show you properly later. I also want you to give me the likelihood ratio test. Again, this is a test to determine the performance of the model. Okay. And I also want you to give me the world test. Last time I told you that the world test is just like the t-test, to determine the partial significance. So normally when the t-test is bigger than the critical value, you reject the null hypothesis of insignificance and conclude that the variable is significant in determining the dependent variable. This time, I want you to give me the world test, which is for logistic. And then I want you to now print all the results here. Print the star summary, print the odds, print the everything, and show me the results. So please run this. When you run this, you're going to get this beautiful results. You got to run and be sure that you got it, not because the results are showing for you. Okay, so that you know. It has given us everything that we need. Everything, everything, everything. So if, for example, in an exam, I'm going to generate something like what you see on your screen, and then I'm going to ask you a series of questions. And I'm going to ask you some of the questions, or most of the questions also here, so that you follow. You can follow it in the slides, and you can follow it here. So all the commands I used to generate this, they are here. Okay, sorry, they're here. All the commands I used to generate this, they are there. And the results, I'm also showing you the results right here. You can also get it in the Python, the Jupyter Notebook. So these are the results. Now let's try to ask some questions related to the results. The first sort of questions you will get, which sometimes you will always get, is to specify the entire regression model based on your regression output using the same labels as Python produced. Using the same labels as Python produced. Now watch this. You have to specify the model. A model specification means that you want beta parameters, you want letters and Greek letters and English letters. So how do you specify the model? This is it. This is how you specify the model. Now, the general logit model, because this is a logit model. The general logit model is given by logit Logit equal to the natural log of the probability of the event happening divided by the probability of the event not happening. We did this last week. That's a general. That's not what your question is asking you. The question is asking you to rather specify for yours. In other words, practicalize it for yours. Okay. And yours goes like this, as you can see here. So you see, ours is you write the logit into bracket, the probability, which is this one. But this one, in our specific case, becomes the beta naught plus beta 1 h. You can see that I have brought I here. I brought I here. Guys, do you feel something is disturbing here? Do you hear some noise here?
No, please.
No.
No noise.
Okay. Okay, so now beta 1 is a coefficient for age. Beta 2 is a coefficient for gender male. Now here I couldn't use underscore. The reason is because I'm writing in Markdown, Python Markdown, Jupyter Markdown. And Markdown, when you use underscore, it recognizes it like a formula. So that's why I use the minus to make it visible. Otherwise, it will make the M a subscript. It sees it as a subscript, more or less. So I've put an I there to indicate that this can change across individuals. This I means that the thing is changing across individuals. And then finally, you have the smoker status and then your error term. This is what we call the specification of the regression model. You will get this many times in your exams as well. So, and of course, when you are writing your thesis, your dissertation, this is the same thing you will do if you have this kind of data. Specifying the regression model is not the same as writing the estimated regression equation. Because watch this. The next part is to write the estimated regression equation. The estimated regression equation simply means you are substituting the coefficient into the model, wherever you see the betas. So you are only replacing the betas from the original model with the actual numbers. And where will you get the actual numbers? When you go up here, okay, to the model here, you see that there is a column called coefficient. So the first one, which is the intercept, that becomes a beta naught. The second one is the beta 1. The third one is the beta 2. The next one is the beta 3. So each coefficient will represent the betas. So you just have to come to the coefficient section and then use it to write the equation. And then, oh, come on. So you write this equation, as you can see, I've done here, okay? And then you substitute the numbers. You can see that I have used the numbers that are exactly in the Python results. So when I give you the table, I'm expecting you to use the numbers unless I've specifically said use 2 decimal places. In that case, this first one would have been 2.73. And this one would have been 0.04. If it had said use 2 decimal places. But until it is saying that, you use all the information. This is the estimated regression, logistic regression equation. Now the next part says write the logistic probability equation. You see, this is a logit model, but not the logit probability equation. The probability equation is different from the logit model itself. The probability equation is going to be, in this case, for the diseased. And then I even added that by converting the log odds into a probability. So here, you write it simply, you are just writing the equation. Okay, and that is just P equal to 1 divided by 1 plus the exponent of all of this. It is this minus, don't forget that it is a minus Z. It is exponent raised to the power, or E raised to the power minus Z. That's what you see there. When you convert that E raised to the power minus Z, you get an exponent. So you can see that I am putting all the values there. This as it is. Okay. And I could have attached it, all right, but here I've used dot to represent each one. And that's it. So these 3 questions are questions if you know how to write them for your specific data you will get in yours. Of course, you'll be given a storyline, a preamble before you get the data set. Any question? No questions so far. Before I go to the next ones. Okay, the next thing is to know how to interpret the model. How do you interpret the model? Now, interpretation of the model is key, is serious, because the way you interpret logic models or logistic regression models are not the same as that of the multiple regression. So let's take the intercept. The intercept is negative 2.729. What does that mean? Well, as you can see, we normally say that if everything is not there, the intercept becomes the baseline. So if there is no age, female or non-smoker, you see what was there was male. What was there was smoker. So these are what make up the baseline. And in terms of the numerical value, the baseline is 0. If it is a number, the baseline is 0. So, and it's negative. So it means that the baseline group, referring to anything that is not in the original model, has a very low disease risk. Okay, this one, in other words, it's not even beautiful to interpret this one, but I'm just doing it because normally it's for cosmetic purposes. The most important ones are the actual regressors or the predictors. So let's go to the actual predictors. The first one. The first one is the age coefficient. As you can see, I'm not talking about what you see here. I'm talking about this one here. Okay, these ones here. And that's the same thing that you have. The coefficient for age is 0.04. 0.04. And let's go to the model so that you can feel it. So it's here, it's 0.04. Okay. And when you look at its p-value is 0.09. If you round it up, okay, it's almost up, almost 10%. Almost 10%. We'll come back to that. But what does a 0.04 coefficient mean? Well, if you want to understand that, you need to connect it to other things. So what it means is that on average, if you should hold all other factors constant, now for you to be able to better interpret it, you need to take the odds, the log odds of this variable. And last time I showed you, so you have to take a calculator and actually calculate, okay, e raised to the power that value, e raised to the power this value. And when you calculate e raised to the power, and you can always get it on your calculator, e raised to the power this value, you're going to get 1.044, which is what you see on the screen here. 1.044. So that is what you're going to interpret. What does that mean? What does this value mean? Well, you always interpret it with the value above the 1 and multiply the value above the 1 by a percentage. And the value above the 1 is the 0.044. 0.44, you multiply it by 100, that'll give you 4.4. So what you're interpreting is actually the 4.4. What is that? We say that on average, given all the other factors, okay, an extra year, because you're talking about age, an additional year of a patient will increase the disease odds. In other words, it will increase the odds of getting a disease. as you know, if you are aging, the likelihood of you getting a particular disease like pressure and those things is high. So every year, the chances of getting a disease increase, okay? The odds of getting a disease. So that's why we say the disease odds. The word odds must come. It increases the odds of getting the disease by 4.4%. 4.4. And this is because we have calculated the odds ratio as 1.044. So the 0.44 is multiplied by 100, and I've done the calculation down here. It's multiplied by 100, and that actually gives it. Now, another way of doing it is do this value minus 1, and whatever you get to multiply by 100%, and you get it in percent. So what this value here means is that every year, okay, every 1 year increase in the age will increase the odds of the disease by 4.42%. That is what. So learn to interpret the coefficient. It's not the same as the multiple regression. It focuses on the odds of the dependent happening, the success variable. But that was a coefficient, that was age. And you see, age is an integer. Age is a continuous variable. And so when you interpret it, age is increasing and falling. Is increasing. So to actually interpret it like that works. But when it is gender is basically not really increasing and falling. You are either 8. And when I say increasing or falling, I mean generally speaking, within a year. And normally this increasing, we just restrict it to within a year is a thing increasing or falling. Gender is not increasing or falling within a year. Okay. So how will you interpret gender? It's a binary variable. So you say that on average, holding other factors constant. And by the way, first thing you do is that you take this value and you take the exponent of that value, and that will give you this number 2.386. 2.386. So in principle, after 1, the value is 138 points, blah, blah, blah. Okay. But I'm still going to use the actual value to interpret. Doesn't matter. Okay. So, I'm just showing you different ways of interpretation. Remember that gender male is a binary. So what you would say is that not the particular disease, not the disease, but then the odds of the disease is expected to be more, not to increase per se, because we are talking about gender. We are talking about a kind of a static variable. It's not a dynamic variable like age. So it's expected to be more by a factor of the answer here. Okay. By a factor of 2.38 when the person is male than when the person is female. Okay. In other words, the disease odd is predicted to be, it's predicted to be more, or is predicted to be higher by a factor of 2.386. Or in this case, it's predicted to be higher by 138.6%. If the patient is a male than if the patient is a female. In other words, the males are more likely to have a higher, disease, whichever the disease is, than females are. Basically, that's what it's trying to say. But remember that even though you have the coefficient, you are supposed to calculate the odds ratio, okay, which is E raised to the power 0.869, and use that answer to do your interpretation. I want to check the formula here. You see, the odds ratio are also there. Okay, the odds ratio, you can see that they are there. but then I would delete them in an exam. So you are supposed to calculate them, which I've shown you how to calculate. E raised to the power the coefficient will give you the odds ratio. So you should use that to be able to do your interpretation. Okay. Let's go to, I'm doing it for all, but normally I wouldn't do. So this one is basically saying that males have 2.386 times higher odds of being diseased than females. That's another way of putting it. Okay, the males have 2.386 times higher odds of being diseased than female. What about smoking status? If you check the coefficient, you see that the smoking status coefficient is 1.336. And now if you want to interpret it, you got to, do E raised to the power that number. And that will give you 3.8 thereabout. So what does that mean? It was for smoker. It wasn't for non-smoker. So you are going to compare the smoker and have the non-smoker as the reference category. So you see that smokers have 3.807 times, odds, okay, of being diseased than non-smokers. Okay, the smokers have 3.807 times higher odds of being diseased. The reason why it's higher is because it's positive. Higher odds of being diseased than female. And then you can see this. Another way of saying it is that smokers have 3.807 higher odds of being diseased than non-smokers. I think it's the same thing I said. Basically, learn how to interpret the coefficient, but not the coefficient, but the odds ratio. The odds ratio. Connect it to the target variable. Connect the odds ratio of each guy to the target variable. Okay, I told you that we also have the coefficient. We also have T statistic. Okay, the T statistic is normally for multiple regression, but for our simple regression, we don't use the T statistic. Sorry, for our logistic regression, we rather use the world test. I wanted to give you the formula for the world test, but it's not too necessary. So you will get a world test in your results. And when you are writing your thesis, you should generate it. The world test is like t-test. It checks whether a coefficient is significantly different from 0. In other words, it checks whether a coefficient is important, significant, or unimportant, insignificant. For example, does this particular predictor have an effect on the outcome? That's what it's trying to answer. Okay. And if the world test is big, that's a big deal. If it's small, that's not a big deal. So let's take an example of the word for age. So let's say that the word for age, okay, I've shown it here. Okay, so let's say the word test for age is 2 point blah, blah, blah. The word test or the T statistic you would have said for normal regression. For gender is this, and then for smoker status is that. What does this mean? Let's take the odd test for age, which is 2.83. What does that mean? Okay, and when you check the p-value, it is significant at 10%. I've indicated here that it is not significant at 5%. Guys, when I say significant at 10%, what I mean is that I'm looking at the p-value here. And when you convert this one, I say it's significant at 10% because this value is less than 10%. If you want to know, multiply it by 100% and you see that is 9%. So when it is 9%, we say it's significant at 10%. When it is 8%, we say it's significant at 10%. When it is 7%, it's significant at 10%. When it is 5%, 4%, 1%, 2%, it is not significant. It is significant at 5%. So now, because there are only 3 of them that you deal with, 10%, 5%, actually 4 of them, 1%, and finally 0.1%. And we always want it to be significant at 0.1%. That means you have a wonderful work. Okay. So the first thing is that this coefficient for age is not significant at 5%, but it's marginally significant at 10%. Why did I use the word marginally? Why did I say marginally significant at 10%? Who has a clue? Marginally.
Because it's almost 10%.
Exactly. It's almost. When would I have not said marginally? When would I have said it is significant at 10%? When the value was what?
Something like 0.6.
Exactly. Okay, so that is
0.06.
no, not 0.06 exactly. So when it is 6%, 7%, yes, you can now choose to say that it is significant at 10%. Okay. So now, I know some of you are listening, but so age shows a very weak evidence, as you can see, because it's not significant at 5%. But not just that, because it's not significant, we can say that it shows a weak evidence of increasing the probability of the disease. In other words, as you age, the probability of you getting the disease is higher. But given what we are getting, there is a weak probability of getting the disease. But at least you are still likely to get a disease as you age. So another way of saying it for proper understanding is that older people, what is this? Older people are more likely to be diseased. That's it. That's what this one is showing because it's positive. But the evidence is not very strong with this small sample that we are using. And guys, when you check the data, you see that this data is just 35 observations. That's not much at all. According to the central limit theorem, it should be very large. So that may explain why. This is just the coefficient, the word test value. The next one is the gender male. Again, that is 1%, but look at that one. Look at the p-value. The p-value is 28%, way more than, by the way, for your information, the p-value is the actual error you make in the research. Actual error you make in the analysis. And so is actual error. You are not supposed to make an error. First of all, 0 errors. But to make 28% errors, it means that, that's a big deal. But it's positive. So the fact that it's positive, we can say that being a male, would have actually potentially generated disease. You're more likely to be diseased if you're a male than a female. But it is not significant at all. So because of that, we'll say that, being a male does not significantly change the log odds of being diseased in this particular example. And that is because it's not significant. Finally, and this is our interpretation using the word test. And again, let me just go back here and show you something about the word test. If you check the word test, this is the coefficient we are dealing with. Okay, and this is it's not a coefficient, it's a t statistic. Okay, and this is a p-value. So you can see that the p-value for the constant is 3%, for the age is 9%, for the gender is 28%, and then for the smoker is almost 9% as well. So the word test is not giving us a very good deal. The last one is the smokers. So you can see that smokers have a higher odds of being diseased. If you check this, it's positive, but the statistical evidence is moderate. You can see that one was just like the age. It's not that strong. So, and again, it is all probably due to the small data set that we have. So we can summarize these things so that for your understanding, okay? For example, in this example, those that are significant was just the intercept. Those that are significant at 10%. If you are significant at 5%, you're automatically significant at 10%. Okay. So you can see that the last one, smokers, okay, is significant at 10%. So smokers somewhat, you see the way we put it, because it was close to 10%. Somewhat, are more likely to be diseased, smokers. And then the male gender or being a male is a predictor, but not a strong predictor of being diseased. So this is key. This is how you interpret your model. Now, is the model good? Is the model good? What shows that it's bad or good? In the multiple regression, we use the R squared. Here we use the pseudo R squared. And that's the formula for the pseudo R. It simply tells you how better your model predicts compared to an empty model. Okay, it tells you the variation in the target as a result of the variability in the predictors. And the way you calculate it is using this formula that you see here. Now, how do you interpret the McFadden? The McFadden, if the value is between 0 and 1, it means your model is weak, Papa. But anything above 4, it means that in practice, your model is outstanding. What is our own? Our own was not outstanding. If you look at it here, our McFadden pseudo R square is 17.8, almost 18%. And that, according to the chart, shows that it is weak to moderate model. And again, part of the reason is because you have 35 observations. Guys, some of you, if your supervisors have not told you, don't go and collect a company data. Always make sure that your variables are many. Your observations are many. So start collecting data now. Start collecting data now. Start collecting data now. Because to use, small samples. Somebody says, oh, I'm going to do for Fidelity Bank. I'm going to do for EcoBank. What is that? So if your samples are companies, you can't use one company. Unless your samples are human beings within a company. If they are human beings within a company, you're going to more than 20,000 human beings. For example, MTN subscribers over millions. Then you have enough data points to do your work. Otherwise, you get these kind of results we are getting. Okay, so this is a very bad, result for the R squared. But it doesn't mean that it's bad. It's moderate. It shows that the model improves upon the null by just 18%. Weak to moderate explanatory power. Okay. This is acceptable, because our data is small, so it's acceptable. But what it means is that if you should include other predictors apart from age, other predictors like BMI, body mass index, diagnosis history of the person, the blood pressure of a person, the lifestyle of a person, any other factors, if you should include them, they are more likely, those factors are more likely to increase our pseudo square. Okay, another thing you can use apart from the pseudo R square is a log likelihood ratio. The log likelihood ratio. Ours is 8.79. And you will see all of this in your result. Okay. So this is a pseudo R square, is in the result. This is a log likelihood statistic, is also there. So when you talk about something you don't see, you see it in the result. Now, our predictors were just 3: age, gender, smokers, just 3. So if you compare the log likelihood to the chi-square distribution with 3 degrees of freedom, okay, you will note that at the 5% level, okay, it is going to be 7.8. Now, our own that we had was 8.79, which is bigger than the critical value of 7.8. Now, take note of something here. If you go up to the result, you are not giving the critical value. So if the question is talking, the question is going to give you the critical value to be able to make your case. Okay. So in our case, the model is statistically significant at the 5% level. You can see clearly that the test statistic exceeds the critical value. So what it means is that at least one feature significant, at least one. One of them significantly improves the model beyond the intercept alone. That is why, so that one alone is helping the others. In our case, you will notice that it's not one, it's two, even though it's at 10% alpha level. Two variables were doing that. So you can see that smoking status and age shows marginal significance, even though gender was insignificant. But combined, they improve the model fit. And that is why the log likelihood ratio is powerful. Okay. Now, let's go to prediction. So sometimes you are asked, what are the chances of being diseased if a patient is 45 years old? So the age has been given. Male smoker, the gender has been given, and the smoking status have been given. So they are asking you to put it back into the model. So the person is 45. Go to the Logistic model. You see that it's 45, so you put 45 here. And then the person is male. Male means that you see, you are either male, which is 1, or female, which is 0. In this case, the person is male, so you put 1 there. But if it had said female, you would have put 0 there. Then you also told that the smoking status of the person is a smoker, not a non-smoker. If it was a non-smoker, you would have put 0. If it is a smoker, you put 1. So you put all of this into the observed equation and then multiply through, and you see that your Logistic value is going to be 1.42. Now, this is a Logistic value. Remember the way you calculate probability. Okay, the probability is 1 divided by 1 plus the exponent of the Logistic value, the z. Okay, so normally last time when we were looking at it, we called it z. In fact, we actually call it minus z or minus y, whichever one. So all you got to do is to take the exponent of the value and remember to bring the minus attached to it. And then add it to 1 and then take the inverse of that answer. And that will give you 80.6. That will be the probability. So remember, you need to get a Logistic and substitute the Logistic into the probability formula. And then that gives you the probability. You see, the question actually mentioned probability, but if you don't take it, you will see what are the chances. Chances here means probability. You could have said, what are the likelihood? What is the likelihood? Or what is the probability of being diseased? It's the same thing. If you do that, you're in good shape. And now, what does that mean? So you will now say that a 45-year-old male smoker has 80.6% chance of being diseased. That's what it means. You are combining everything. This is called prediction. Okay, so you can use these results to do prediction. Sometimes some people will tell you that, oh, we don't use statistical models like this to do prediction. It's machine learning alone. No. Before machine learning came, this is what we were using, and it's still relevant. The machine learning is just going to corroborate. Okay, so prediction, you can use this for your prediction. So if you want to predict a particular outcome, I'm telling you, you can do it. This is beautiful. Okay, now so that is all about inferences. Now let's go to the prediction properly. I'm going back to the model. All of these things we've done. Okay. So it's cool. So this, if you are doing prediction, you don't use this start model, use the scikit-learn. That's another package that you will use. In fact, it was in the model when I was loading it. So these are all the commands, and then you will get the following results. So let me just walk you through the commands quickly. So first, the model is going to do is a logistic regression. That's what you can see here. We are still going to fit the train model and then the test model. Sorry, the train of the dependent variable, which is a y, and then the predictors, which is an x. We'll train them. And then we'll create a predictive y and then a y probability. Now, this is very important. We are going to use Y predicting when we are going to do confusion metrics, and we shall talk about confusion metrics. So let's say that you want to predict the value of Y. Here, Y is the probability of getting it. Y is actually disease. But we don't want that. We want a probability of getting disease. Okay. So this one will give you a yes or no decision, like a doctor saying that you have a disease, you don't have a disease. It's very, very good to get that because you can use it to calculate certain things, which we shall come to, especially in something known as confusion metrics. But why not go for the probability of the model? This one, it gives you a risk score. So the doctor told you that you have a disease, but then this one is telling you that the doctor is actually telling you that there is 81% chance of you having the disease. So it's not just that you have a disease. You see, this you have a disease is just 1 or 0. But then this second one actually tells you the exact. You see, now you are talking about 81%. So you know that you are closer to 1 or you're closer to 0. This is powerful, guys. This is solid for research, solid for your exams. So you are going to use this one to calculate something known as ROC curve and AUC curve and choosing thresholds and things. That is why I have both of them for you. We will also calculate the confusion matrix. I'll tell you a lot about the confusion matrix very soon. But let me move away and go and talk a bit about confusion matrix and why it is called confusion. Anytime you have the word confusion, it's when your brain scatterbruta, your brain is confused. You don't know which is which. The confusion matrix is basically a 2x2 table matrix. We use it to check how well a classification model is performing. And logistic model is a typical example of a classification model. How is it performing? Let's compare the actual values of the disease, okay, which is the true disease status, versus the predicted values of the disease, what the model is telling us. Let's compare the two. So we use the confusion matrix. It's called confusion because the classification decision needs to be, it's called confusion because when you look at it, you have to choose between positive and negative and positive. That's what brings the word confusion. But why are we using it for logistic regression? Because logistic regression, it deals with labels, categories. So you using the confusion matrix, you can answer questions like this. How many predictions were correct? You're going to do that now. How many were wrong? What type of mistake did the model make? Okay, that's where the confusion comes in. And that is why we're going to do this. So let's take an example before we come to our own. Anytime you're comparing prediction, for example, let's say that I predict right now, you don't have a disease, so it's 0. Then I predicted that when you are 30 years. When you are 50 years, you will get a disease. Okay. And now you get to 50 years and you don't have the disease. It means that the prediction was what? It means that prediction was what?
Was wrong.
It was wrong. Okay. You got a wrong prediction. So there is a table that will show you which is which and which is not which. Now, what were you predicting? You are predicting me having the disease. But you could also have predicted me not having the disease. And you could be right and you could be wrong in both cases. That is why we have 4 columns. That's why we say it's a 2x2. Let's take them in detail. So there are 4 possible outcomes here. The top part are the predictions. The far left part are the actuals. So if you predict, okay, that there's going to be positive, okay, and that is 1, okay, you predict 1. 1 here means you predict that the person will be diseased. And then we check the actual, the person is actually having the disease. Then we are in this area. So your prediction becomes positive. So you predicted positive and it was actually true. So this becomes true positive. True positive. You predicted 1, that is a positive. And it was actually 1. So it is true positive. But here in this section here, What are you predicting? You are predicting negative, 0. And it turns out to be what? Positive when you look here. Okay. You are predicting negative, but it turns out to be positive. So your prediction becomes a false positive. It's a wrong prediction. A false positive. Now, when you look here, you are predicting again. I think this one shouldn't be false positive. This one should be false negative, guys. It should be Fn, and then Fp comes here. You realize that? Yeah. Fn, Fp. Just a second. Let me just quickly alter that so that. So you are predicting, if you look here, for example, you are predicting that the person will have the disease. That's the one here. Okay. And the person actually didn't have the disease. That's 0. Okay. So you are predicting that a person will have the disease. The person did not have the disease. So your prediction is wrong. False positive. False positive. Yeah, and you can have different updates. So the model, the key point is that if you want true negatives, so when your true negatives, when your true positives and your true negatives are bigger, that is when we like it. The model will predict the disease, and then it's actually a disease. So this is a typical example of predicting positive, which is 1, and then you actually get positive. That's a true positive. Like that. Okay. When I put in the figures, then it will make sense. Okay. Now, the confusion matrix is a table summarizing the 4 outcomes. Confusion because it tells you where the model gets confused. Confuses positives as negatives, which is a false negative, and confuses negatives as positive, okay, which is a false positive. These concepts matter because they affect accuracy, prediction, recall, and F1. We shall look at that soon. Okay, so this is a typical example of a confusion matrix for our case. Now, let me go back here. We are going to tell the model to estimate the confusion matrix for us. Watch it here. We are estimating the confusion matrix not on the trained data. In fact, even the prediction crowd was not on the trained data, it's on the test data. Okay, everything is on the test data. Okay, it is on the test data. So if your model is truly good, let's apply it to the testing data and see whether it's truly good. So we are going to generate a confusion matrix here. And then we'll create something called classification report. It's the same thing. It will just report the whole thing beautifully for us. And then finally, we'll use a certain graph to tell us where we have gone positive, where we are going away, whether what we did was right or not. One of the graphs is known as ROC and AUC. We'll talk about them very soon. Okay. Now, let me go back here. Once you have your true positive, true negative, there are a lot of things you can calculate. You can calculate something called accuracy. Guys, you can be asked to rather calculate the accuracy yourself in the exams. Once you have the TP, the true positive, the true negative, you calculating the accuracy is easy. Okay. Your accuracy is the percentage of cases that were correctly specified. That's all. Okay. And how do you find that? It is a true positive plus the true negative divided by the positive and the negative. Okay. That's it. That's your accuracy. It tells you, was the model able to correctly classify the people as disease or not disease? The next thing you could be asked to calculate is the precision. That is that proportion of the cases that the classifier labeled as positive are actually what? Positive. That's precision. In other words, of all the predicted positives, how many were truly positives? The precision is calculated by true positive divided by true positive plus false positive. You see, if you don't take care, your ears will be positive, negative, negative. That's where the confusion is. That's why it's called confusion matrix. The next thing you could be asked to calculate, you will be asked to calculate, is actually the recall or the sensitivity. Again, it is that portion of the cases, all of them, that the positive cases were classified as positive. Now, if you don't take it, you might think that is the same as precision, but look at the difference. It's the percentage of the cases that the percentage of the cases that the positive cases were classified as positive. Okay. In other words, you look at this, of all the predictors for the precision, of all the positives, how many were correct? This one says of all the actual positive, not predicted positive, not predicted, but the actual positives, no? How many were correct? Okay. So whereas precision is looking at the predicted guys, recall is like going back. And going back, you are going back to original. And original is actual. Recall is looking at the actuals. Okay. Look at them. They are all having TP at the top. Okay. When it comes down, they are all having TP at the down. But on the right, one is having false positives, the other is having false negatives. That is a record. And then you also have another, all of this will evaluate your model, or whether your model is strong or not strong. You have specificity. In other words, of all the actual negatives, how many were truly negative? It's just like, okay, it's just like recall. Okay, look at it. It's just like recall. Recall is Tn over Tn plus Fp. Specificity. Now, some of this formula can be confusing. And so if it is a formula that you need, this formula will be given to you if it's in an exam. But if it is a normal dissertation you are writing, you should know it yourself. Okay. Where do positive or negative sign and coefficient come in? Every logistic regression will have a coefficient. Okay. So positive coefficient will increase the log of the odds. And we know that once you find the log of the odds, you can find the probability because they're connected. So it will increase the probability, and then it means that it's more likely to be positive. So positive coefficient has got a connection with a positive case. And negative coefficient has got a connection with a negative case or a negative prediction. So in our case, this is the answer, but let me not show you the answer first. Let me just go to the result. So now we are going to run this entire result and then also show this and show some other evaluation metrics. In fact, I'll show you something here that these matrices, you don't need them. You don't need them, to be honest. Let me just remove them. Micro, I don't need it. Okay. But I'm just bringing that for a reason. So we'll run this. There you go. So these are the results. First, let's look at the confusion matrix. It is 4115. That's the confusion matrix. Okay. And as you know, the 41 is, you see, the way it has been arranged, you should know clearly. Sometimes it may have been swapped. Sometimes it can be swapped. So this is it, 41. You can see that I brought the zeros here. I brought the zeros. At first, it was 1. If you check here, the previous one, it was 1 coming first. But here, I brought the zeros here. So take note. It doesn't matter much. The only thing that has swapped is this one and then that one. So it is 4115. Okay, so what does the first 4 mean? Okay, and it is true negative here. So it means that 4 people who are actually not diseased, that's a negative. Okay, not disease is 0. They are actually not negative. Not disease. And the model correctly predicted that they are not diseased. So the model has been able to predict nicely that 4 healthy people were correctly predicted as being healthy. That's what this part is saying. Then you go to F1, FP. Where's that? FP here, and that's 1. People who are not diseased, you can see it there for the actual. Actual here means that 0. They are not diseased. If they are diseased, they will be 1. They are not diseased. Okay, but the model predicted 1 for them. Okay, so it means that the model is saying that they are diseased. So the person is not diseased. The model is saying that they are diseased. So the model is wrong. That is false positive. You tell me that he's positively diseased, but that is false positive. So the model falsely, worried one healthy person. Now the model is doing well here with a 4, but he's worrying 1 person. He's doing well with a 4 people, but he's worried. Yeah. Then we go to FN. Okay. The one on the bottom left. The FN is saying that is 1, which means that the model is saying that 1 person is diseased. Okay. And what did it say? 1 person is diseased. So what is it? 1 person is diseased. Was a person actually diseased? Was a person actually diseased or not? Hey.
Yes, the person was diseased.
Person was diseased.
Yes.
But the model predicted.
The model says was the person diseased or not?
Yes.
Yes.
Did the model say the person was diseased?
Yes.
No.
No, the model predicted it wasn't. The person wasn't diseased.
Yeah.
So the person was diseased, and the model has said that the person, the person was diseased, and the model said that the person was not diseased. That is dangerous. That is dangerous. Why is this dangerous? Because in medicine, particularly, okay, what you are doing is that you're going to kill the person. We need to solve the problem, and you're not making the problem solvable. And then the last one, that one is good. The model is doing well, but it's not doing well in the other things. The last one is the TP, which is 5, true positive. So the people who are actually diseased, okay, and the model correctly predicted that they are diseased. And that was the highest number. Okay. So in this case, the model has passed. He caught 5 disease cases correctly. The model has passed. And you can see that the first one, the model has also passed there. So the passes are getting better. Guys, when you're doing your thesis, you see that the numbers will be bigger than what you're seeing here. Okay. Now, you should be able to use these ones to calculate if you have this formula. So for example, if I say that, let's just go to accuracy. Okay, accuracy is TP plus TN. What is TP? 5. What is TN? 4. So 4 plus 5 is what? 9. And then it says divided by P plus N. So the total P is here. P is when you look at all of these one here. Okay. Total positives, okay, here. And then total negatives, that is here. So let's use that to calculate one of them. I mean, you can do one of them and then match it against the result I'm about to show you. So this is the precision formula. Of course, it's in the result as well. So when you check accuracy, accuracy is what? Okay, accuracy is 82%. This is accuracy. It's 82% in all angles. How did you get the 82%? How did you get it?
9 divided by 11.
When you take your calculator, you are very right because the total cases is 11. Okay, so it is going to be 9 divided by 11. Guys, take your calculator and confirm. And you see that averagely that is 82%. This is exactly what you will calculate, but I'm showing you the answer here. But then in the exam, you will have to calculate yourself. Because once I have given you this table, even this table, there's a way you can come out of it manually, but I won't give it to you manually. I'll calculate with you. Then I'll let you use the formula to calculate the accuracy yourself. Now, what do you think will be the value for the precision? TP. What was the value for TP? precision. What's the value for TP? 5.
5.
And what's the value for FP? FP is 1. So what will be the precision?
0.83.
83%, isn't it? And again, when you come here, you will see that precision is 83%. And we are talking about precision for the disease cases. Okay, so that's why I'm talking about precision for 1. Okay, precision for the disease cases. That is it. If you want it for the not disease cases, that's going to be that 80. So you can use that to get the precision, which is 83. Now you can use the same thing to also get. Hey, I think I made a typo here. Yeah, I made a typo. I call this one precision, even though it's supposed to be recall. Okay. This one is supposed to be recall. I don't know why I called it that. So again, it is going to be the same as the previous one, but it will not be +1. This one is FP, and this one is FN. And then they're supposed to be the same because they are 1, 1. So again, when you check recall, it's also going to be what? 83, just like the precision. The F1 score is going to be the same thing as that. Okay. Where is that? So you have the F1 score, and then you have the support. The support for the not disease is 5. Because when you come here, you add 4 + 1, that is 5. For the disease, is going to be 6. That is 1 + 5, that is 6. That's what the software will also. And the totals are the ones that are here. When you add the 5 + 6, you get a total set. So all of these are known as the classification method. But what do they mean generally? So we can conclude by saying that here, 82% accuracy indicates that the model correctly identified 82% of the real disease cases. And out of all the predicted cases, how many of them were actually diseased? That is what this value has actually given you, 82%. And then for the precision of all the diseased people, how many did we detect? The diseased ones. We had 83%. The record was 83%. Okay. And the rest were all 83% in this very example. So the model is correctly doing what. If you look at the specificity, that was 80%. Okay, you can see that here. That's this, which is the same as the F score. That is 80%. Okay. And then when you look at the mistakes it made, out of the 11, it misclassifies 2. Okay, we saw that there were 1, 1 across the corners. So out of the 11, it misclassifies 2, but then it classified correctly 9 of them. So the confusion matrix reveals strong predictive behavior and balanced performance in this very example. But here's a mistake it did. It missed 1 diseased person. That's serious. In medicine, it's not a joke. Okay, missing. Let's say that somebody has COVID, and you miss that person who has COVID, and you say that the person doesn't have COVID when the person actually has COVID. The person goes to stay in the church. That person is going to supply COVID to a lot of people. So missing a disease is usually worse than giving a false alarm. I mean, it's better to say that the person doesn't have COVID. It's better to say that the person has COVID. Then you quarantine the person. Then later on, we do a check. We realize that the person didn't even have COVID. That is better. That's a false alarm. It's better than to actually say that the person does not have COVID when he actually has COVID. Very good. Imagine somebody has been predicted that he doesn't have HIV, and he's going about and then supplying it. All right. Now, there is something we call. So now, how good is your model? You use 2 things, the ROC and the AUC. The ROC is a curve. The AUC is a number. They all come from these calculations we have made. Let's get a bit of an understanding of these two, and then we'll be wrapping up today. ROC stands for Receiver Operating Characteristics. It is a plot, as you can see up there. It is plotting true positive rates, TPR. Okay, it's on this vertical axis, true positive rate against false positive rate. Now, the true positive rate is on the y-axis, the false positive rate is on the x-axis. It tells you how the model is behaving under different tolerance rates. So if you're actually calculating, it is going to be the integral of the true positive rate, the total positive rate, and the false positive rate, and the differential of the false positive rate. Okay. This formula, forget about it much. But if you are writing a dissertation, you should document it. So that's the ROC. So when you look at the ROC and you check the value, the ROC is, this is a perfect match of the true positive versus false positive. But the ROC clearly goes up here, gets here, and where it cuts, the red line at the upper level, that is the value you're looking for. And it goes higher. It casts it at a very high point there. And we'll explain that very soon. The explanation is that when you have the AUC, it's telling you the probability that the model ranks a random diseased person higher than a random healthy person. That's what it's telling you. What is the probability that the model, someone is diseased and is ranked higher, okay, and someone is rather healthy, and that person has been ranked lower. So when you have an AUC value of 1, that is perfect separation. You've separated the people, the diseased people versus the non-diseased people. You've done a good job. And please note that we are talking about disease, non-disease. It can be anything. Loan, those who default in loan and those who don't default in loan. Those who churn and those who don't churn. Those who cancel subscription and those who don't cancel subscription. You know, those who vote for MPP and those who don't vote, things like that. When you separate them correctly, because it's difficult to separate minds, then AUC value is what? Is 1. But when it is in the middle, it means that there's a guess. But when it is below 5%, 50%, it means that the model is worse than the guess, the random guess. So you want the AUC value to always be closer to 1. It's just like the R square to be closer to 1. Okay, so ours was what? Was closer to 1. It was almost 97%. So in our case, we can say that our model can correctly distinguish between disease and healthy people. 97% of the time is able to do that. And you can see the curve hugs. Okay, that's the hugging, the blue curve and the red curve, they hug together, okay, at the top left corner, which is the ideal classifier. The model also hardly confuses positive and negatives. It made a slide this thing, but it doesn't confuse it too much. Okay. So in English, if you were to write this thing for your dissertation, you would have said that a logistic model achieved an AUC value of 97%, indicating excellent discriminatory power. This means that 97% of random pairs consistent of one disease and one non-disease individual. The model assigns a higher predictive probability to the disease case. Okay. An AUC value of above 90% is considered as standard in classification tax. I've already said this, confirming that in our case, our model is reliably distinguishes between disease and healthy people across all threshold values. Okay, so this is one way to determine the power of your model. And you can see that so far, our model is doing well. One last thing. Sometimes some people use MAE, MAPE, so many things. These are some of them. But here's my caution. Don't use them. Logistic regression is not a regression problem. It is a classification problem. So a regression problem is where you use minimum absolute error mean squared error, root mean squared error, and all of those things. You don't use that here. What do you use? What you use is what we have said above. You use the ROC, you use the AUC. And these two are the things that guides you in your work. But there's one more thing you use. That one is allowed in logistic regression, and that is known as the log loss. Log loss. What is that? Log loss. Oh, log loss. What does that mean? As you can see, there's a word called loss. It's one of the best probability metrics for logistic regression. If you have the AUC, ROC, and log loss, it's enough. Okay. By the way, nobody asked me what is the AUC. It is the area under the ROC curve. That is the AUC. This one. AUC is area under the ROC curve. I don't know whether I wrote it somewhere. Okay. Area under the ROC curve. Now let's go back to log loss. This is a formula for you to just entertain yourself with when you're writing your thesis. It doesn't mean you should memorize it. Okay. Now, lower values are better. Okay. So when the values are lower, it means that there's a better calibrated probability prediction. The probability. So what is it? It tells you how well your model's predicted probabilities match the actual labels. Okay. Our value, if you check up here, our log loss value is, there's it. We use a cross entropy. It is 0.5, which is almost 50% or 51%. So our value is fairly good. It's in the middle. Because when you look at the range, okay, when it is up to 20%, smaller value is better. Okay. So when it is up to, because it's a loss, you don't want, so when you have less loss, it's better. So up to 20% is excellent probability prediction. Good calibration is between 20% to 50%. Okay, 50% to 10 is acceptable, but we need to improve. 1% is bad, very, very bad. So you want a log loss ratio that is smaller. And that is how you execute. If you want to use, show your work in a form of a journal paper, this is how you show your work in a journal paper. It has for causality purposes, but for prediction purposes, those are the ones that you see here. Please, I've just shown you one curve. There are about 5 different curves you can use for your work. Ladies and gentlemen, that brings us to the end of the entire